So what we have here are three tanks in series, each draining by gravity. Each of these three tanks is identical, so they have the same cross-sectional area as well as the same area at their outlet, and they are all initially fed by, or rather tank 1 is initially fed by a Q in, and each subsequent tank is fed through by gravity. So what we aim to do here is we want to take our initial differential equation, so something that looks like this. So we have some area times our dH dt, which gives us basically gives us our differential volume with respect to time. And this is equal to our volumetric flow rate flowing into the first tank minus, by Bernoulli's equation, we have this relationship that kind of describes the gravity effects of the draining. My cursor disappeared. So square root 2g times the area of our outlet times our height to the 1/2. So this is the balance that we have derived in previous videos to allow us to do analyses of the tank effects as we give impulses to the initial Q in or kind of mess around with the cross-sectional areas. But today's goal is I want to take this differential equation and have it linearized so we can apply a Laplace transform to relate the tank height in tank 3 to our initial inflow. So what do I mean by linearize? Well, if we want to do a Laplace transform to this differential equation, we absolutely need to have a linear differential equation, which means that the power of our variable of interest must be 1. As it stands right now, the power right now is 1/2. So what we can do is we can kind of rewrite this differential equation to give us a deviation variable that is to the first power and do our Laplace transform based on that variable. So that is the goal for this first part. And the first step is I'm going to isolate our dH dt term. So 1 over a times our Q in minus, what I'm going to do here, just to make things simpler, these are just a set of constants, and I'm going to define them as alpha. So minus alpha h to the 1/2. Now, what we must do here is we need to rewrite this h to the 1/2 in terms of a difference between an initial steady state and the value at time t. So in order to do that, I'm going to rewrite this section out here. So minus, this should also get an area. So alpha over a, alpha over a. So what ends up happening is that we have the initial steady state value, so h bar to the 1/2. This bar signifies the initial steady state. And to that, we add the derivative of, so basically the instantaneous slope. So that'll be 1 over 2 square root h bar times the difference. And that difference is what we are going to define as our h prime. So the h prime is emblematic of our height at time equals t minus the initial steady state. So the height at the initial steady state. So this is what that stands for. And because of that, we now rewrite our differential term in terms of that deviation from the initial steady state. So now what we must do here is we must find the value at that initial steady state and then subtract that from this newly derived equation. So what do I mean by that? What I mean is when our dH dt is equal to 0, rather if our dH prime dt is equal to 0, this means that our h prime, so h minus h bar, are equal to each other. So since these are equal, if you took the difference of these two, you would get 0. And so essentially, this term here would not exist. So if we set that derivative equal to 0, what we end up getting, we have this 1 over a term, and this q becomes the q at the initial steady state. So we define that with the bar. Minus alpha over a times height at the initial steady state to the 1/2 power. Now what we end up doing is we subtract this equation that is for our initial steady state from this deviation equation that we have derived. So if we were to do that, what we would end up getting is that we have we have some q at time t, and then we also have the q at the steady state. So this kind of becomes a q prime of sorts. So I'll say something like dh prime dt equals 1 over a times q in prime. So this is now the deviation for a time-dependent variable. Minus alpha over a times h prime over 2 root h bar. So now what we end up having is a linear differential equation by using this deviation term for our time-dependent variables. And now what we can go ahead and do is we can take the Laplace transform of each of these terms. So the Laplace transform of a derivative is going to be s times h, and we'll take the Laplace transform of this. So what we get here is a capital Q minus, how do I write this? I guess I can do, so alpha over 2a h bar times capital H. So now this is our Laplace transform by linearizing this differential equation for our system. So the next step is I'm going to want to get this in terms of h. So what I'll do is I'll get this over to this side and pull out the h. So that's going to give us s plus alpha 2a h bar equals 1 over a times q in, divide over. So now we get h equals q in over, so a times s, and then that will cancel here. So plus alpha 2 there. And then what I'm going to want to do is I'll divide each of the terms on the top and the bottom by alpha over 2h. And that'll give me, so this is going to be 2h bar alpha over 2ah bar over alpha times s plus 1. Now, what we have here is a first order transfer function, and that is because this s is to the first power. And for first order transfer functions, we have a generalized standard form, which is that we have some k representative of our gain times tau, which is a time constant, times s plus 1. So this is the standard form for our first order transfer function. So now if we were to go over and translate this in terms of our derived transfer function for the height, what we have is that our k is equal to 2 times h bar over alpha, and our tau, our time constant, is equal to 2a root h bar over alpha. So this is the transfer function that relates, oh, don't want to forget your flow. So this is the transfer function that relates our height to our flow. So the next step is going to be drawing out a block diagram and going backwards from h3 to qn to give us the overall transfer function that defines that relationship. Before we get to that, we want to do one more analysis. And that analysis is going to be, what about the flows exiting each tank? How do we relate that to the subsequent height? And that's actually pretty simple because we have another set of differential equations to help us tackle that. So let's say I want to figure out, oh boy, so Q1 is going to be equal to alpha h1 to the 1/2. So this Q1 is related to the height of the previous tank and then the gravity effects controlled by our outlet point. Just to keep this simple, I'll just do this in terms of like a QI. So I'll keep Q1 there, but this kind of relates for each and every stream. So the first step is we need to linearize this. So we get Q1 equals alpha times h bar to the 1/2 plus h prime over 2 h bar, very similar to what we did before. Then we want to find our steady state solution. So we get Q1 bar is equal to alpha h bar to the 1/2, which means that our deviation variable defined for the same system is going to be equal to alpha h prime over 2 root h bar. Then we want to do our Laplace transform. So now what we have is we have our Q is equal to alpha over 2 root h bar times h. So there we go. Now we've also related our flow back to our height. In a very similar sense, though, we see that we defined our k as 2 root h bar over alpha. Over here, we have alpha over 2 root h bar. So we say that, hey, this is similar to what we had before. This is actually just 1 over k. So that's the coefficient that brings us back from our flow to our height. So right now we have two sets of equations. We have an equation that takes us from a height and brings us to a flow, brings it to a flow characteristic. And then we also have another equation that brings us from a flow characteristic back to the height characteristic. And these are the variables that make that happen. So let's go here. And so let's just start with, so we have this process and exiting it, we have H3. So to get to H3, we must first find that height using Q2. So using this relationship. So from going from Q to H is going to give us, or we're going to have to use 1 over K. So going from Q2 to H3, we must use 1 over K. Before that, we have a height 2. So we have H2 here. Well, how do we get from heights to flow? It's this relationship here, our K over tau S plus 1. So K over tau S plus 1. And after this, it gets a little bit repetitive, but we will go through it just to be able, or rather just to check our work as we go along, make sure we're not making any mistakes. So now what we have is we have a Q1 that feeds into our height 2. So that's going to be defined by 1 over K. And before Q1, we have a height 1 that is defined by K over tau S plus 1. And then feeding into our height 1 is our Qn. So we use 1 over K to get over. So why did I even draw all this out? Well, so you see that in order to get to H3, we multiply Q2 by 1 over K. But Q2 is equal to H2 times K over tau S plus 1. And H2 is equal to Q1 over 1. So by substituting in each one of these variables, we get a final relationship that takes us from Qn to H3, which looks something like this. So H3 is equal to 1. Which way should we go? Should we go backwards or forward? Let's go forwards. Qn times 1 over K times K over tau S plus 1. And remember that each of these streams are identical because we made the problem as such. The only thing that differs is the height within each of the tanks. If we had different streams running at different flow rates or running at different cross-sectional areas, then we would have to define which stream we are actually calculating the gain and the time constant for. But since these are identical, what we can go ahead and do is start canceling out these k's once we've drawn out the entire function. But for right now, let's just go through these one by one. So after that, we get another 1 over k times k over tau S plus 1. 1 over k. I feel like I've screwed up somewhere. Oh, all right. These are backwards. I was looking at them in terms of getting from Q to H, but really we should be looking at it the other way. So to get from H to Q, we have tau, or K over tau S plus 1. So rather, these are all backwards, unfortunately. To get back from Q to H, it's 1 over K. And then K over tau S plus 1. 1 over K. Then K over tau S plus 1. Now that makes a little bit more sense. So really what ends up happening is we start with K over tau S plus 1. Bring this here. And then that last term will also be K over tau S plus 1. That looks a little bit better. And the reason is as such. So I'll show you. We're going to cancel out these K's. This one stays. And our final relationship looks like this. We have K over tau S plus 1 cubed times Qn. So what we have now is actually a third order transfer function, which makes sense because in order to get to our final tank height, we need to go through 3 different tanks. So there are 3 orders in order to get to our height in tank 3, which is why it wasn't making sense initially. It was drawing out to just be a second order transfer function instead of a first order transfer function, or rather a third order transfer function, which is how I was able to catch that mistake. But now what we have is a transfer function that gives us a relationship between the tank, the level of tank 3 to the initial inlet. So I've outlined another block diagram here, and I'm just going to walk through it really quick. So this GP here is indicative of our process, and that process is what we had before with our 3 tanks in series. So I'm consolidating that into just one block here. So we have an output of our height in tank 3, and then we have an input of our inlet flow. In this case, what ends up happening is that this inlet flow is now controlled by this proportional controller with gain Kc. This controller takes an input of our error, and that error is a function of this comparator where we feed in our tank height in tank 3, or rather our level in tank 3, and our set point. It'll take those 2 values, compute the error, feed that into the proportional controller, which will try to mitigate that error by changing the value of our Qn and eventually affecting the value of our height in the third tank. To simplify this down a little bit, essentially what we have now is we have a process with feedback control. So we have H3 out and we have HSP, so our set point height in. So if we were to go through this process like always, what we would find is H3, right here is fine. H3 is equal to, so GP times KC times E. And we know, we write this like this, that our error is equal to our set point minus the height in the third tank. So now if we were to multiply this out, what we would have is H3 1 plus KCGP is equal to KCGP times HSP. And if you notice, G with feedback control is equal to our well, maybe let's not do it that way. I think it might be easier to just do the relationship of these two values, because essentially what ends up happening is that we have some sort of multiplication going on here. So our H3 times GFB equals HSP. So to find GFB, we want to find HSP over H3. So if we were to do that, okay, here's my mistake. This should be, so HSP times GFB equals H3. So GFB has to be equal H3 over HSP. And so I was actually right here. This should be HSP minus H3, which gives me, which gives me this. And now if I want to find H3 over HSP, what we end up getting is KCGP over 1 plus KCGP. Right. So now we found our value for GFB. So this is our process with the feedback control. So what I'll do now, I'm going to get H3 by itself. So H3, draw that better, equals KCGP 1 plus KCGP times HSP. We know what the transfer function for our process is. We already derived that. So we can go ahead and grab that again. So that's going to be K over tau S plus 1. 1 plus K tau S plus 1 cubed, remember, for each of these. So times our set point height. And what we'll do now is we're going to multiply, I guess, the numerator and denominator by our tau S plus 1 term. So if we do that here, we get tau S plus 1 cubed plus K over, I'll give myself a little bit more room here. Over KC, which is our proportional only controller, times the gain of our process, times our height at the set point. So now this is the transfer function for our system with the feedback only controller, relating our level in tank 3 to our set point height. And we have introduced this KC, which is the proportional only controller gain, into our function. So slight algebraic mistake I caught myself on is that we have a KC here, so that KC should show up in the rest of our expressions. So this is right now. So now let's go off and say something like, well, what if we had a step change, so a unit step change for our HSP, which is to say that our HSP equals 1 over S. So that'll give us a step change. Well, we can go ahead and we'll say something like, so H3, I'm going to change this now to the deviation variable, equal to KC times K tau S plus 1 cubed plus KC K times 1 over S is basically what we're saying. So we have a deviation now. We changed our set point by unit step of 1. And now we basically want to find, well, what is going to be our final value for our deviation. So we can go ahead and introduce something called the final value theorem, FVT for short. And that's going to be something like, if we have, so our step times our function, so this is in our Laplace domain, that's going to be equal, if we take the limit of this as s approaches 0, that's going to be equal to the value of our function at time equals infinity. So the final value of our function. And that can be directly applied to what we have here. So what we have now, we're going to have an SH3 prime. I don't know. What's the best way to write this? So this is going to be our SY. And what we want to do is we want to take the limit. I really don't want to write it that way. So let's just say I'm going to bring this S over to here, and I'm going to define this as my Y. So I'm going to make this a bit more symbolic, I guess. What we're saying is that if we take the limit as S approaches 0 of this, that's going to give us the limit as t approaches infinity of our deviation variable for tank 3. So let's go ahead and bring this over to this side. I'm going to move this out of the way. So just going to keep this over there. So basically we are saying that if we want to find the limit as t approaches infinity of h3 prime, we need to find the limit as s approaches 0 of kc times k. So basically this transfer function we've derived. So if we go ahead and do that, the only term that has s, and the reason that we don't have the 1 over s anymore is because we've multiplied it over to this side to meet this requirement for final value theorem. The only thing that has s is in our tau s term. So if that is 0, then this term equals 0, and we're left with 1 cubed is equal to 1. So what we are left with is Kc. So our proportional gain times our process gain. 1 plus Kc K. So this is our deviation for our time equal infinity for our height in tank 3. And if we were to do just a quick little analysis, as we increase the proportional controller gain, as we increase this 1 becomes negligible and this value here becomes 1, which is what we expect. If we do a unit step change of 1, then we expect our deviation to also be 1 at the final value state. However, as we decrease this proportional controller gain all the way down, this 1 in the denominator becomes dominant. So what ends up happening is that we never actually reach our set point. It becomes an asymptotic relationship to our set point. So yeah, that is a Laplace transform analysis for our 3-tank system.